Good morning, students. Hopefully, audio video is okay.
Yes, sir.
So, in last class, we have started gamma distribution or means continuous random variable. In that, we have studied uh, exponential family or gamma family. In that, we have till now we have covered the exponential distribution and the gamma distribution. And most important theorem you have seen about the exponential distribution is memoryless property. And another important theorem is if the interoccurrence time follow the Poisson distribution or exponential distribution. If the interoccurrence time follow the exponential distribution, then occurrences of event follow the Poisson distribution. Or if the occurrences of the events follow the Poisson distribution, then interoccurrence time follow the exponential distribution. Then if xi are independent exponential variate, then the sum of n exponential variate follow the gamma distribution. So that important theorems we have seen in last class. Now next is chi-square distribution. So this is another gamma family distribution. In this, if you put in the gamma family, if you put lambda is equal to half and r is equal to n by 2, if you put lambda is equal to half and r is equal to n by 2, so the given gamma variate change into the chi-square variate. So here we have x follow a continuous random variable follow the chi-square distribution with parameter n, and here the parameter n are known parameter n is known as degree of freedom. Instead of the parameter, we call it as a degree of freedom. Degree of freedom implies that we have we have the freedom to choose the n value, right? We have the freedom to choose the n value. It is also a continuous random variable and member of the exponential family or the gamma family. Just in the pdf of you have to put lambda is equal to half and r is equal to n by 2. You will get the pdf for the gamma distribution as x to power n by 2 minus 1 e to power minus x by 2 upon 2 to power n by 2 gamma of n by 2 when x greater than 0, otherwise it is 0. So here you have seen, right? So just in this pdf you have to put, right, lambda is equal to half and r is equal to n by 2. So you will get the pdf for the exponential distribution. And now from here, what will be the ex? R is equal to n by 2 and lambda is equal to 1 by 2. So it will become n, right? So variance of x will be the r is equal to n by 2 and lambda is equal to 1 by 4. So it will become the n by or 2n, right? Variance of chi square will become the 2x. Similarly, here when we put mxt, so lambda is equal to 1 by 2 and r is equal to n by 2. So it will become 1 minus 2t to power n by 2, right? So here we have the all the indices. So here we have the ex is equal to n, vx is equal to 2n, and mxt is equal to 1 minus 2t to power minus n by 2 for t less than 1 by 2. Actually, whatever the application we will study, in all application are the multivariable. That's why we are studying mainly the additive property. So here another the additive property for the chi-square distribution is if x1, x2, xn are independent. Most important, all the multivariable in the multivariable system, the variable must be independent. Are independent, chi-squared. Chi-squared notation is like this, right? This is the notation of the chi-square. So if the x1, x2, xn are independent, chi-square variate with degree of freedom, n1, n2, nn. Then x1 plus x2 plus xn will also have the chi-square distribution with degree of freedom n1 plus n2 plus nn. So what is given to you? Xi follow the chi-square distribution with degree of freedom ni. With degree of freedom ni, it is given to you, and so we know that its moment generating function mxi, moment generating function for the random variable xi, is 1 minus 2t to power minus ni by 2, minus ni by 2, and I can be 1, 2 or n. And if the x1, x2, xn are independent and their sum is equal to x, right? If the x is equal to x1 plus x2 plus xn, then moment generating function for the x is equal to, right, moment generating function for x is equal to product of moment generating function for xit, right? I vary from 1 to n. So here we have the mxt is equal to mx1t into mx2t into mxnt, and it we know that what is the moment generating function for the xi, since xi follow the chi-square distribution, so it is equal to 1 minus 2t to power minus n by n1 by 2, 1 minus 2t to power minus n2 by 2, and dash 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 1 minus 2t to power minus nn by 2, which can be written as 1 minus 2t to power minus n1 plus n2 plus nn by 2. So you can see the moment generating function is nothing, it is a fingerprint, right? Fingerprint for any random variable or any distribution. So from here we can judge, or this expression prompt us that the random variable x follow the chi-square distribution, right? Fingerprint means for all the variable, for all the random variable, for all the distribution, we have the unique, for each and every random variable and distribution, we have the unique moment generating function. So from here we can judge x follow the chi-square distribution with degree of freedom n, where uh, n is sum of n1 n2 and nn. Now main application of the chi-square distribution is in the statistical analysis. Whenever we have to compare the two population, right, whenever we have to compare the variance of two population, there we have the use of this chi-square distribution. Now some more important theorem. If x has an exponential distribution, x has an exponential distribution with parameter lambda, so when I am saying that x follow the exponential distribution with parameter lambda, it means fx lambda is pdf is the lambda e to power minus lambda x. So now you have to determine, then 2 lambda x has chi-square distribution with degree of freedom 2, with degree of freedom 2. So it is given to you x follow the exponential distribution with parameter lambda. So its pdf is given by fx is equal to lambda e to power minus lambda x for x greater than 0, and for the exponential distribution moment generating function is lambda upon lambda minus t, where t is less than lambda. Then you define the random variable y, you define the random variable y as 2 lambda x. So when we define, since x is a random variable, their algebra is also a random variable. So let y is equal to 2 lambda x. Then we know that the moment, if you have to write the moment generating function, so moment generating function for the m for the y, so m y t, m y, and y is what, 2 lambda x t, which can be written as, mx of 2 lambda t, mx of the 2 lambda t, and mx is what, mx is the e of e to power tx, and instead of the t, now we have the 2 lambda t, 2 lambda t, and expectation, we know that it is the integration value into probability. So e to power, e to power 2 lambda t into x value into probability, because x follow the exponential distribution, so into pdf lambda e to power minus lambda x dx. So which lambda, if you take outside, so lambda, right, integral 0 to infinity e to power minus lambda x into 1 minus 2t dx, and on integration it will give you 1 upon 1 minus 2t. So 1 upon 1 minus 2t can be written as 1 minus 2t minus 2 upon 2, minus 2 upon 2. So this 2 is what? It is the n, degree of freedom, right? Degree of freedom. So now you can say that y follow, and this expression match as a, moment generating function for the chi-square distribution. So now you can say that, you can judge that y follow the chi-square distribution with degree of freedom, right? With the degree of freedom 2. So is there any doubt in the derivation? Anyone? How I am driving? I'm using the basic properties to determine the distribution for the function of the random variable. Yes, one student is asking. Please. Yes, who is asking? Please, you can ask. Yes, Ram, sir. Is there any doubt?
No, sir. Sorry.
No problem. No problem. Now, if x1, x2, xn are independent exponential variate means, now you can see that xi follow the exponential distribution. Exponential distribution with same parameter lambda means all the xi, right, for I is equal to 1 to n. If x1, x2, xn are the independent exponential variate with same parameter lambda, then prove that 2 lambda into sum of exponential variate x1 plus x2 plus xn will have chi-square distribution with degree of freedom 2n. So let us define a variable of random variable s, right, as a sum of random variables, function of the random variables. So let us define this s as sum of exponential variate, sum of exponential variate as x1 plus x2 plus xn. And if you compute the moment, because from we know that moment generating function is the fingerprint, so for all the distribution we compute the moment generating function only. Mean, variance, standard deviation, pdf may be different for the two distribution, but moment generating function is the unique. So if you compute the moment generating function for the s, so this will become m of x1 plus x2 plus xn t, which can be written as product of mxi, that is mx1t into mx2t into mxnt. And for the exponential distribution, we know that if you have to write the mxi, so for the exponential distribution, moment generating function is lambda upon lambda minus t for t less than lambda. For the t less than lambda. So here we have written lambda upon lambda minus t corresponding to x1, lambda upon lambda minus t corresponding to x2, and lambda upon lambda minus t corresponding to xn. So that will give you lambda, that will give you the lambda upon lambda minus t to power n. But we have to compute the moment generating function for the 2 lambda s. So moment generating function for 2 lambda s by the theory of moment generating function, it will become ms of 2 lambda t. Ms of 2 lambda t, right? Means we know that moment generating function for the s is lambda upon lambda minus t to power n. Instead of the t, just you replace by the 2 lambda t. So it will become lambda upon lambda minus 2 lambda t to power n. So from all we can cancel lambda, 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 which can be written as 1 minus 2t to power minus n. So this can be written as 1 minus 2t to power minus 2n upon 2. 2n upon 2. So from here we can say that 2 lambda s follow the chi-square distribution with degree of freedom 2n. Right? With degree of freedom 2n. Now, if just now I have to, or in previous class I have told you that if the x1, x2, xn follow the exponential distribution, then their sum follow the which distribution? Anyone? If the x1, x2, xn are independent exponential variate, then x1 plus x2 plus xn follow the gamma distribution, right? It follow the gamma distribution with parameter n and lambda. So now if I say that x has gamma distribution with parameter n and lambda, so 2 lambda x means 2 lambda, this is what? This is the x. So 2 lambda x also follow the same chi-square distribution with degree of freedom 2n. So that is the another theorem. It is the same thing, right? So if x has gamma distribution with parameter n and lambda, then 2 lambda x will have chi-square distribution with degree of freedom 2n. So moment generating function for the gamma distribution is lambda upon lambda minus t to power n. So moment generating function for the 2 lambda x is nothing. It is the moment generating function for the x corresponding to 2 lambda t, which can be written as, this is the minus, right? This is the 1 minus 2t to power minus n, right? This is the minus n. So which can be written as 1 minus 2t to power minus 2n upon 2. So here we say that the 2 lambda x follow the chi-square distribution with parameter chi-square distribution with degree of freedom 2 lambda x follow the chi-square distribution with degree of freedom 2n. Now you already know the normal variate is most important distribution in statistics or in probability theory, right? Because in many statistical analysis we use this this distribution. This is also known as the Gaussian distribution. So if you say that a random variable x, so first of all x is the continuous random variable, right? First we should know whether it is the continuous random variable or the discrete random variable. So x is the continuous random variable, or normal variate is continuous random variable with parameter mu and sigma square, with parameter mu and sigma square, and its PDF is given by 1 upon sigma root of 2 pi e to power minus half x minus mu upon sigma whole square, where x lie between minus infinity to infinity. X lie between minus infinity to infinity. Mu also lie between minus infinity to infinity, and sigma is always positive. So the shape of normal distribution is the bell shape, right? The shape of normal distribution is bell shape, and it is symmetric about the mean. It is symmetric about the mean. So here we have the bell shape, right? So in this, what we have, this point, this point is the point of inflection, right? This is the x is equal to mu minus sigma, and this is the x is equal to mu plus sigma. So mu plus minus sigma is point of inflection. These are the point of inflection. Point of inflection. And point of inflection is the stationary point, right, where the derivative is equal to 0. Means this is nothing, this is the mixture of the convex function, and this is the mixture of the concave function, right? This is the mixture of convex or concave function. Means here we have the amalgamation of the minimum point or the maximum point. That's why it is the stationary point. At the, you know that at the means maximum, the first derivative is equal to 0. At the minimum also, the first derivative is equal to 0, right? So point of inflection is the amalgamation of the maxima minima. Clear this part? So here it is concave downward for x minus mu less than mod of x minus mu less than sigma, right? So it is the concave downward, right? And it is the convex upward, yeah, or concave upward, right, for mod of x minus mu greater than or greater than sigma. So that is the x is equal to mu plus sigma, known as the point of inflection. The mean for the normal variate is equal to mu, and variance for normal variate is equal to sigma square. And moment generating function for the normal variate mxt is equal to e to power mu t plus half sigma square t square. And normal, a normal distribution, that's why its name is the normal. For the normal distribution, the mean is equal to median is equal to mod. Here the x is equal to mu, right? X is equal to mu is mean as well as median and mod also for the normal variate. If the normal variate for the normal distribution, if mu is equal to 0 and sigma square is equal to 1, or sigma is equal to 1, right, because sigma is always positive, so the x is termed as the z, and z is nothing, it is the standard standard normal variate, standard normal variate. So here z follow the normal distribution or standard normal distribution with mean 0 and variance 1, with mean 0 and the variance 1. And here z is equal to x minus mu upon sigma. So when in this, if you put the mu is equal to 0 and sigma is equal to 1, sigma is equal to 1. So our and x is equal to z, and x is equal to z. So the PDF is given by the fz. And in case of the standard distribution, we in general, instead of writing the fz, we prefer the phi z. So phi z, the PDF for the standard normal variate, PDF for the standard normal variate phi z will become 1 upon square root of 2 pi e to power minus z square by 2, where z vary from minus infinity to infinity, and its CDF we denote by the capital Fz, and capital Fz is we kept for the standard normal variate, we denote the capital Fz as a capital phi z, capital phi z, that is the accumulation of the probability up to that point. So p z less than equal to z, that is the integral minus infinity to z of PDF, right? That is the integral minus infinity to z of phi z dz, and that is 1 upon root 2 pi e to power minus z square by 2 dz. And we know that normal variate is symmetric about the mean. Symmetric about the mean, it means if it is the standard normal variate, so it is symmetric about the mean. So and it vary from minus infinity to infinity. So at the z is equal to 0, we have the half probability. So that's why the f0 or capital phi of 0 is equal to half. Now, if x follow the normal distribution with parameter mu and sigma square, and we are defining the new random variable y as linear combination ax plus b, where a and b are linear constant. Since x is the normal variate, or random variable, so algebra of the random variable is also the random variable. So y is also random variable. So when y is a random variable, we have to determine the distribution of the this. So y also follow the normal distribution with mean a mu plus b, and variance a square sigma square, and the variance a square sigma square. Now if x follow the normal distribution with parameter mu and sigma square, and you define the z as x minus mu upon sigma, which can be written as 1 upon sigma into x plus minus mu upon sigma, which can be written as like this. So this is what? This is the A, this is B. So using above theorem, right? It can be written as, it means Z follow the, right? From here, if you write, so Z follow the normal distribution with mean, right? So a mu plus b, so that will give you the 0, plus a square sigma square, that will give you 1, right? So this follow the standard normal distribution with parameter 0 and 1. In case of the normal variate, if you have to determine the required probability, we can use the CDF, and in all the book, you will find at least one statistical table that is for the standard normal variate. I will tell you why it is so. So here, if x follow the normal variate with parameter mu and sigma square, and a and b are real number, right? And if you have to determine the probability of x lie between a to b, then it is equal to FV minus FA, right? FV minus FA. Or if you write this as a minus mu, x minus mu, and b minus mu, then divide by sigma, divide by sigma, divide by sigma. So this is nothing, this is the z, standard normal variate. So it will be the p of a minus mu upon sigma less than z less than b minus mu upon sigma, which can be written as phi of phi of phi of b minus mu upon sigma and minus phi of a minus mu upon sigma. So that's why by one table you can determine the probability, right? Required probability for any mu, for any sigma, for any x. With one table, after converting in such a way, you can determine the required probability for any mu, for any sigma, and for any x. Another important property for the normal variate is phi of minus z. Phi of minus z is equal to 1 minus phi of z, right? Phi of z. Here it is written f of minus z is equal to 1 minus fz. Means f or phi are both same thing. Both are representing the CDF. Just to highlight that it is the standard normal variate, we are writing the capital phi instead of the capital F. So f of minus z by definition, right? F is what? CDF. CDF is what? Accumulation of the probability up to that point. So probability that z less than equal to minus z. Since normal variate is symmetric, since normal variate is symmetric about the mean, so if it is the minus z, so the probability less than minus z is equal to probability greater than plus z. That since the normal variate is symmetric about the mean, so probability of the z less than equal to minus z can be written as probability of the z greater than z. So by the theory of the probability, it can be written as 1 minus probability of the z less than z, that is the 1 minus fz, right? That is the 1 minus fz. So it is very important property. Generally we have the table in all the book, we have the table for the positive z only. So with this approach, you can write the probability for the negative z also, because the z vary from minus infinity to infinity. So you can from the given value of the positive z, you can determine the required probability for the negative z also easily. Another important relation is if z follow the standard normal distribution with parameter 0 and 1. 0 and 1 means this is the mu and this is the sigma square. Then z square of standard normal variate, square of normal random variate, because z is the standard normal variate, so their square is also the random variable. Their square is also the random variable. So z square follow the chi-square distribution with degree of freedom 1. With degree of freedom 1. So here we define the random variable y as z square, and we know that for for recognizing which distribution it is following, right? We use the characteristic, characteristic of the moment identity function, since moment identity function is the fingerprint. So we here compute the m by t. m by t, by definition it is the expectation of e to power t by. So it will be the e to power t z square, y is equal to z square. Clear? So this will become because z is what? It is a standard normal variate. So this will become value into probability, right? Value into probability. So value into probability, right? So minus infinity to infinity, value e to power t z square into PDF. PDF is 1 upon root of 2 pi e to power minus half z square dz. Now here if you substitute, here when you substitute z is equal to, right, z is equal to or u is equal to z root of 1 minus 2t, u is equal to z into root of 1 minus 2t. So m by t will be the 1 upon root 1 upon root of 2 pi integral minus infinity to infinity, right, e to power minus half z square 1 minus 2t dz, right? So using the gamma variate, right, this is nothing, this is the 1 minus 1 minus 2t to power minus half. So this is nothing, this is the moment generating function for the chi-square distribution, right? So here the degree of freedom will become the, it implies that y follow the chi-square distribution with degree of freedom 1. Now additive property of the normal distribution. Now next is additive property of additive property of normal distribution or normal variate, normal variate. Let x1 x2 xn be normal variate with parameter with parameter I. Let's say xi follow the normal distribution with parameter mu I and sigma I square, and independent. Then if you define another random variable y as a linear sum, means a1 x1 plus a2 x2 plus an xn, then y follow the normal distribution with parameter a1 mu1 plus a2 mu2 plus an mu1, and the variance a1 square sigma 1 square plus a2 square sigma 2 square plus an square sigma n square. Let us understand this by the example. Let x1 x2 x3 follow the normal distribution, right? So e of x1 is given to you as a 2, e of x2 is given to you as a 3, and e of x3 is given to you as a 4. Variance of x1 is given to you as a 1, variance of x2 is given to you 1, and variance of x3 is given to you as a 2. You have another random variable y as 2x1 minus 3x2 minus x3. So e of y will be what? E of y will be the what? It is the a1, right? E of x1 plus a2, e of x2 plus a3, e of x3. And here the a1 is what? 2, a2 is what? Minus 3, and A3 is what? -1. And E of x1 is given to you as a 2, E of x2 is given to you as a 3, and E of x3 is given to you as a 4. And here we have the plus. So that it will give you 4 minus 9 minus 4, right? That is the 4 minus 9 minus 4, that is equal to -9. And similarly, the variance for the y is what? It is the a1 square variance of x1 plus a2 square variance of x2 plus a3 square variance of x3. In general, we have seen in the exam, you do the mistake here only. So here the a1, a2, a3 are what? 2 minus 3 minus 1. So 2 square minus 3 square minus 1 square. And variance is given to you as a 1, 1 and 2. And here we have the plus. In general, in exam, you write the here minus. Right? So this will become 4, 4 into 1, 9 into 1 and 1 into 2. So that will be the 15. So in this way, we compute the distribution of the algebra of normal variate. Now, another important theorem is central limit theorem. So, with the help of the central limit theorem, you can determine the required probability for any distribution, right? Through one table, that is the standard normal table. That's why in all statistical or operation research book, you will find one table, at least one table, that is for the standard normal variate. With the help of the central limit theorem, you can determine the required probability for any distribution through the standard normal table. So what is the central limit theorem? Central limit theorem is, let x1, x2, xn be the sequence of independent random variable with mean mu I and variance sigma I square. I vary from 1 to n. Let us define the sum x1 plus x2 plus xn under the certain general condition which hold in most of the cases. Right? If you define the sum of an independent variable, right? Then another random variable you are defining, the Zn. Zn is equal to Sn minus sum of mean divided by square root of sum of the variance. So always follow the standard normal distribution. Means here the xi can be any distribution. In most of the case, it is true. Xi Sn is what? The sum of xi's. And xi can follow the any distribution. Right? So generally, when we have the n is very large, in general, it is true, right? It is true when n is very large, and by convention, we assume that n must be more than 25. So, for example, if x follow the binomial distribution with parameter n and p, so we know that for the binomial distribution, mean is what? Np. Variance is what? Npq. So if you take x minus mean upon square root of the variance, so x minus np upon root of npq, follow the standard normal distribution. That is the application. Means whether you have the table of the binomial distribution or not, you can determine the required probability through the standard normal variate or standard normal table. For example, if x follow the Poisson distribution with parameter lambda, you know that x is what? It is a discrete random variable. Here the binomial is what? It is also the discrete random variable, right? So we know that for the Poisson distribution, Ex is what? Lambda, and variance of x is what? It is also lambda. So if you take the x minus lambda upon x minus mean upon square root of the variance, right? Also follow the standard normal variate. So, right? So that is the beauty of the central limit theorem. Whether we have the continuous random variable or the discrete random variable, just with the help of the one standard normal variate table, right, or distribution table, we can determine the required probability using right. So all these are the approximation. Approximately we can determine, not exact. Clear? Now another important distribution is the uniform distribution. This is the last distribution. So here you can say that if x is equal to a, here we have the x is equal to b. So for taking any value, we have the equal probability. We have equal probability, and that probability is nothing 1 minus b upon a. 1 minus b upon a. So here we say that that's why its name is the uniform, right? Because we uniformly it is distributed with the same probability it is distributed. You can take any value of x, right, with the same probability. So if the x follow the uniform distribution with parameter a and b, then its pdf is given by 1 upon b minus a, where x can take any value between a to b. So corresponding cdf is what? Right, 0 if x is less than a, x minus a upon b minus a if x lie between a to b, and 1 when x is greater than b. So this is the cdf. I'm not going in the derivation part. And its mean and variance are given by the a plus b by 2 and b minus a whole square by 12. And moment generating function for the uniform variate is 1 upon b minus a into e to power bt minus e to power at upon t, when t is not equal to 0. When t is equal to 0, then it is equal to 1. Clear? So these are the some standard distribution. So in evening class we continue from here. So today I will finish the basic of the probability. So next class is very important, because in means next to next class, tomorrow morning class, tomorrow 10 o'clock class is very important, because at that time I will start the queuing theory, the first chapter or application, right? Or it is means very important lecture. Tomorrow lecture is very important. Today I will finish the basic of the probability.
Sir, can you scroll up a bit?
Pardon?
Can you scroll up a bit, sir, for that formula for MXFT? Yes, sir. Yes, sir. Thank you.
So all these distribution I will use now directly, just by naming that this distribution I'm using. Any other doubt? Now you can leave if you haven't doubt. If you have doubt, you can open your mic and ask the doubt.